Hi everyone, welcome to AWM Graduate Student Seminar. Today we have two speakers. The first one is Arnaja Mitra. She is a PhD student from the University of Texas at Dallas, and her talk today is Equivariant Global Hopf bifurcation in abstract nonlinear parabolic problems. And our second speaker is Isabel Barrio Sanchez. She is a PhD student from the University of Pittsburgh, and her talk is New Redistribution Scheme for Weighted State Redistribution with Adaptive Mesh Refinements. Our first speaker, Arnaja, can start.
Sure. I hope you can see my screen right now, right?
Yes.
Okay. Thank you for giving the opportunity to share my research here. I'm Arnaja Mitra from the University of Texas at Dallas, and I'm going to explain about the equivariant global Hopf bifurcation in nonlinear parabolic equation. So here is the overview that we will go through. First is the motivation, then setting my problem statement and setting the corresponding functional space. And also we will discuss about the branches of non-constant periodic solution, what is the concept of the crossing number, maximal twisted orbit types, and finally we will reach to the main result. So here is the motivation. What is Hopf bifurcation? So if you have a parameterized dynamical system, then the Hopf bifurcation is just a phenomenon.
The seminar.
Yes. Is the occurrence of the periodic solution when your parameter crosses some critical value. As an example, say you have a simple dynamical system with parameter alpha in such that your alpha 0 is your equilibrium point and your linearization is a continuous map, then the Hopf bifurcation will occur when your equilibrium alpha 0 will change the stability. That means when your parameter alpha will change, your eigenvalue will passes from left to right or right to left. So it's just that means there will be an appearance of a purely imaginary eigenvalue, and that is the Hopf bifurcation occurrence condition. Next, about the application, it has a lot of applications such in the population dynamics, fluid dynamics, modeling of heart conditions, then understanding the neural network and more. Now the main question arises, if you have a symmetries of a dynamical system, then what is the effect of it on its actual dynamics? So that means what about you can say about the existence or the multiplicity of the branches? If it is so, you can think about whether there will exist a global result or global branch? And more of the question is, what about the symmetric properties of the obtained or existent periodic solution? So my research will answer all those questions. So let me approach to it. First is the problems. You have a gamma compact Lie group and the H Hilbert gamma representation and an operator self-adjoint and accretive operator, that means monotone, and gamma equivariant as well. And you have an I as embedding gamma equivariant and a A for continuous map. Then our problem statement is nothing but just the system equation 2, where alpha is your parameter and P is some non-zero constant, and it is a non-negative period P. There are a couple of assumptions for our research. First is alpha 0 is your equilibrium point for the system 2 that we just considered. And we also beta of alpha is denoting the linearization of your right-hand side map F. And we also considered this condition 4. It is just saying that F has an uniformly continuity. And moreover, alpha 0 is non-degenerate. That means the condition 5 is satisfying. And the embedding map I is your compact operator. So these all are our assumptions. So beside going through our reaching to our result, I also built an example to set up your concept parallelly. So in my example, I consider that omega is a subset of R2 is a domain, gamma 1 is a symmetric group of omega. And we consider in this case, my system is equation 2, where my operator is the negative Laplace operator, which is a self-adjoint monotone operator, and also it's a gamma equivariant, here gamma is O2. And moreover, we consider if is an odd function. This we will know, this we will require for the global result. And here I consider my if is alpha eta u and ru, where ru is satisfying this, and eta is a plus ib, and p is a greater than 1 unnatural number such that we satisfy this priori bound. Now let me come back to our theorem. So it says we just consider all the equilibrium point and say denote it E naught, eta naught as my set of all equilibrium point. So now is the characteristic equation. We just consider the corresponding characteristic equation of my system 2. And then just by using the change of variable, we can find out the characteristic equation of our system 2. And correspondingly, we can find out the characteristic space. And similarly, we can find out the algebraic multiplicity as well. Now, the main thing in our degree theory, so in this system, we're using a degree theory method, which is a usual Brouwer degree-based method, but which will depend on an orbit. So in this case, main concept is we need to use the decomposition. So the decomposition for you just first consider all the list of distinct irreducible gamma representation. And then the space what we have for the space V, we will decompose in such a way Vj such that Vj, each of Vj will consist all the equivalent real irreducible representation of nu j, and that is known as it is modeled on nu j. And each of these Vj is known as gamma isotopic decomposition. And similarly, just we remodel that what the eigenspace we have, just take the intersection with our now the decomposition. It is just in partition of V in terms of irreducible representation, and we take the intersection with the eigenspace. Similarly, we modified our algebraic multiplicity by this definition, which is just known as the nu j isotopic multiplicity. And then we just take the restriction of our characteristic function on each of the VJC. Here, VJC is just the complexification of the VJ. And then we assume that alpha naught 0 is an isolated center. So isolated center means if you take a neighborhood around the alpha naught 0, then it contains just alpha naught 0 as a center, no other than that. And moreover, the center means for this alpha, the parameter alpha naught, when your parameter will take alpha naught value, there will an appearance of a purely imaginary eigenvalue. That means there the system will undergoes through an Hopf bifurcation. That is the center. And then we consider just denote by B of alpha naught the set of all beta such that kernel of I beta is not equal to singleton 0. That means you are consisting all your purely imaginary eigenvalue and such beta you are noting it by B of alpha naught. Now, for using the degree theory method, you need to find everything to a functional setup. So whatever setup we did so far, we will just change to the functional space setting. First here, first of all, our space, our group or the symmetry, you can say that is the gamma. So our group is gamma time S1. And then we change all our space. You remember the H, V, and W to all the functional spaces. So this is the functional space. Here H1 to pi is the subloop space. L is denoting the LP spaces. So we just consider the corresponding functional spaces where our action is given by the equation 12. Now we just rescaling our system, that system or our problem statement we have, the problem 2, just introducing a new parameter beta equals to 2 pi over p. So now we are having our remodel or remodified system with two parameter alpha and beta. So if we go back to our parallel example, we just changes everything whatever the space we have to a functional space H and D of this functional space for our operator and the other functional space. And moreover here our gamma is O2 times Z2. And naturally you will see all our assumptions are going to be satisfied for this case. And if you take the linearization of your right hand side, you will get only a alpha eta b, that is the linearization of the system. And you can find out the corresponding characteristic equation as well. So in this case, you will see that your system is becoming just a boundary value problem. And in this case also you can see that lambda naught will be your characteristic value if and only if your alpha eta negative lambda naught is in your spectrum of negative Laplace operator. So now let me come back to our ongoing theory. So now to apply the degree theory, as you transfer everything, all your spaces to a functional space, you need to transfer all your equation or the function to an operator equation. So we introduce our right-hand side by a new operator L beta, which is nothing but the right-hand side function we have. We consider the Nimitsky operator is just which is defined just by f of alpha v of d, just considering the equation to the operator. And then the embedding map that we have, we consider the corresponding embedding operator. And then we introduce that R plus, which is nothing but just the non-negative real number, and R2 plus is your R and R plus, where alpha parameter is in R and beta parameter is in R plus. Then my system, the equation we have will just transform to an operator equation defined by 19, which is just a fixed mapping or fixed point mapping like a function. And now we can see that this is a completely continuous map. And identity minus completely continuous map is known as a completely continuous field. So this is an equivariant completely continuous field, which is one of the requirement to apply the degree theory. And we are satisfying that. Next, we just consider or denote by M the set of all trivial solution of our system. And similarly, as we consider the linearization, now we just consider the linearization of our operator. So now instead of our system, now we have just an operator equation. And similar, that is defined by this, just considering the Nimitsky operator on the linearization, that is the linearization of your operator. And similarly, we just decompose our space according to our linear, like our decomposition, the G representation nu kj, where k is denoting the k Fourier mod or the S1 action. And moreover, similarly, we just consider the restriction of our linearization on each of the decomposition EKJ. Now, if we focus on our parallel example, in our example, we have the operator as negative Laplace operator. We can find out the spectrum. Once we got our spectrum by using the polar coordinate, which is nothing but the nth positive zero of the Bessel function of the first kind, we can find out the eigenspace as well. Similarly, we can see that in this case, our gamma is O2 times Z2. So my G is gamma times S1, that is O2 times Z2 times S1. And you can find out the decomposition of V according to the real irreducible representation, where each of the representation is denoting by that Wj minus is just a notation, and the minus sign is just to denoting that we have a Z2 action. Similarly, in our example, we can find out the restriction of our characteristic operator on the VJC, the decomposition of this VJ, where C is denoting just the simplification of VJ. Now, let me know what is the branch and what is the branch of non-constant periodic solution. First, let me know about what is the non-constant solution. So we denote by P the non-constant solution such that your alpha F is not equal to 0 for such U which does not belongs to V, that is non-constant. Now the branch is nothing but a subset of P such that whose closure is a connected component of P closure and it contains a non-trivial continua. So moreover, if my alpha naught beta naught 0 will belongs to the closure of B and M, that M is a trivial solution set, then I will say that my system 2 will undergoes through an Hopf bifurcation, and moreover, the point alpha naught beta naught 0 will known as an Hopf bifurcation point. Moreover, if alpha naught beta naught 0 is an Hopf bifurcation point, then I will say that alpha naught 0 is a center. That makes sense because we know that a center is nothing but for that fixed parameter value, my system will have a purely imaginary eigenvalue. Yeah, of course, the linearization of the system. And in that case also we can prove that not only beta naught, we will also have I beta naught k for any k natural number is an Hopf bifurcation point. So here is a picture of a developing of a folding branch B. This is a branch which is bifurcating from alpha naught beta naught 0. So this, and which I can see that it is coming back to again another bifurcation point, and again sometimes it can happen that it is coming back and never come back, so it flows out. So the thing is, like our branch can bifurcate from one bifurcating point to another bifurcating point, or it can close up and never come back. So that gives you the concept of local Hopf bifurcation result and the global Hopf bifurcation result. That is our main result. So let me approach to that. First of all, to approaching this, we need another assumption, that is just the local ellipsis condition. And now the projection. So you remember our system, we just have the alpha as a parameter, but not the beta. So we are considering the space which has alpha, beta, both, that is R2 plus R is for alpha and R plus is for beta, that we are knowing as a Fuller space. But our space is without beta, that is R times E, that is our original space. And P is nothing but just the projection of alpha, beta, U on alpha with the alpha and E. If you go back to our picture, that you can see that alpha and E is just our original, this alpha and E is our just the original space. And when we introducing the third line or the third dimension, that is giving you the Fuller space. So this is an important proposition for our result. It says that if a branch is such that exists such that where the projection of that branch is bounded in your original space, then the branch is also bounded in your Fuller space. So the converse statement of this you can think about, that if you have a branch which is unbounded in your Fuller space, then it is unbounded in your original space. So this proposition we will need when we will reach to the global result. So we prove this proposition in our paper. Now, to approach to our main result, we need two main concepts. One is the crossing number and the second is the twisted orbit types. So what is the crossing number? If you consider a small neighborhood around the alpha naught, say alpha minus is denoting the left-hand side of your alpha naught and alpha plus is denoting the right-hand side of your alpha naught. And beta L is such beta, or you can think about for alpha equal to alpha naught, you are having I beta L eigenvalue or a characteristic value. Then T plus will denote all the summation of your algebraic multiplicity, such that if you consider a small neighborhood around I beta L, and T minus for alpha, T minus is for the alpha in left hand side, and for alpha in right hand side, if you consider the neighborhood around the I beta L, then the sum of the algebraic multiplicity will denote by Tj plus. So here Mg is algebraic multiplicity that we came to know. Summation is denoting the small neighborhood around your lambda, that is your I beta L. And then Tj, the crossing number, which is also known as mu J crossing number, is just Tj minus Tj plus. So let me give a small example to think about what is a crossing number. So here is a picture. This is the left-hand side alpha or alpha naught, and this is the right-hand side of your alpha naught. And think about your alpha when it is in the left-hand side of your alpha naught, and you consider a small neighborhood UL around your I beta L, because I beta L is the characteristic value when your alpha is alpha naught. And for that, you have your algebraic multiplicity 4, that is number of total eigenvalue, you have 4. Then in that case, you will have Tj minus is 4. Now, when your alpha cross the alpha naught and pass to the right-hand side of your alpha naught neighborhood, and you got say it changes and it comes to you 2 only number in eigenvalue, then your Tj plus will be 2. So your crossing number is 4 minus 2 is equals to 2. We will not focus on the numerical value of the Tj. We will just need the sign of this Tj or the crossing number. I hope it is clear to you now, the crossing number. Now let's go forward to our parallel example. Think about my system will have a pure Hopf bifurcation. That means there is an appearance of the purely imaginary eigenvalue. And this case is possible when you have your alpha beta value that we can prove by calculation. And similarly, we can find out the total critical set, and we prove that it is a discrete. And moreover, we find out that for such alpha naught beta naught, my Tj is coming -1. That means just to think about that my crossing number is of negative sign, that we will need in our result later. And moreover, we find out that O2 and Dj Z2. These are the two types of orbit we got. What is the orbit? We will come to know in the next slide. And here we also decompose our space in EKJ accordingly to the complexification of WJ minus, just as our theory is set. Now let me focus about the orbit type, twisted orbit, and the maximal twisted orbit. So before going through, just we recall some basic definition that we read already in a group theory. That is, say if H is a subgroup of G and N of H is the normalizer, then the while group is defined by the quotient group of N of H and H. And we know the conjugacy relation is built on A in the such while group. We can find out the conjugacy relation. And moreover, it is a partial order relation. So we can find a chain. And similarly, we can find out the maximal conjugacy class as well. And we can define the phi n by dimension of while group of H is n. So, and we consider all such conjugacy class by phi n g. Now then the twisted subgroup says that it is a subgroup of gamma times S1 such that which satisfies this condition. So where K is a subgroup of gamma and phi is a homomorphism which satisfies this condition. Now what is an orbit? Orbit is nothing but the Gx which is a subset of X where G acts on X. And G suffix X, that is an isotropy or the symmetric group, it is a subgroup of G and which is defined as all those G's as the Gx equals to X. Then the conjugacy class of such isotropy is known as orbit type. So if you consider the conjugacy class of the twisted subgroup, that is your orbit types of twisted orbit types. And as there is a partial order, you can find out the maximal twisted orbit types. And moreover, we don't need to hand calculation to find all these such things. There is a software gap. We use a gap to find out all the orbit types, the maximal twisted orbit types. So let me consider now phi kg is denote the set of all such maximal twisted orbit types. And we defined a function eta kg. You can consider it like a characteristic function based on the conjugacy class k. And moreover, we define a function or map is just a linear combination with the crossing number and this characteristic function like. Now, if we focus on the parallel example, now this TKJ we will need in our example, in our main result. Based on this number, we will create our result. So in example, we saw already that we have two orbit. So and gradually we can find that this is our max twisted orbit. This is a twisted orbit and this is a maximal twisted orbit types. So this we all did by the gap. Next, now is our main result focus. So the local result says that if TKK, that the number we define, that is the linear combination with the characteristic function with the crossing number, if this is non-zero, then I can say that my original system too will undergo through the Hopf bifurcation. And moreover, the fixed point set, that is the branch, that Hopf bifurcation means there absolutely there is a branch, that this K fixed point set BK will have a non-trivial continuum and moreover K will be a subgroup of GU. This gives you that the branch symmetrizes. So we answered that there will be an existence of Hopf bifurcation. We answered that there will be an existence of a branch and the multiplicity also we can calculate. Moreover, we can think, we can say what is the symmetrizes of such branch. The only thing we remain to think about what is the global result. That means whether there will exist an unbounded branch or not, or unbounded solution. So for thinking about that, we will introduce a new action that is Z2 action or the antipodal action. And that's why we consider now my group is gamma naught times Z2. And for that, to omit the constant solution, because we just focus on a non-constant solution, we introduce a subgroup H, which is just a subgroup of gamma naught times Z2 times S1. So instead of just gamma naught S1, we just consider another symmetry Z2. That means we consider there is an antipodal action or my map is odd. We already considered in an example that my A map is odd. That is the reason why we consider just for to get our global result. Now in the example, parallelly, you can focus that we already got our orbit type. We can say that yes, in our result, all the conditions are satisfying. We also see our crossing number is just -1. So we can see that here it is not equal to 0. Therefore, there will be an Hopf bifurcation. There will be an existence of branch. And moreover, we can find out the symmetrices. So this is the symmetrices of such branches for our specific example. Now let me focus to a theory to reach our global result. Here I just considered the H fixed point space of my space E. And you can see where by saying the definition of E, we just omit the constant solution, and that is just for introducing the H. It is up to you how you will consider the subgroup so that you can omit the constant solution. And similarly, everything will be similar. Just we will approach the parallelly just by shifting to H reduced operator, H fixed point space. So whatever the map we have, we kept everything, just make it to H reduced operator. And similarly, we will find out the linearization is very parallel concept. Again, we consider the H critical point, which is denoting by lambda H. And then we consider that this is discrete. In our example, we can prove that H critical set is automatically discrete because our original critical set is discrete. So when you will take the H fixed point, it will also be discrete. Now the global result. This is the revenue types result. This says that if you have all these conditions are satisfied and non-constant, then you will get an open bounded G invariant set such that there will be an Hopf bifurcation point in W but not on the boundary, such that which has a non-empty solution, and moreover is the non-constant solution, and moreover the bifurcation point is finite. And the result you are getting that the TKAK or TKM, the number we defined, is 0. So this result, this is a global result. Based on that, as a consequence, we are getting a very important and beautiful result. It is here. It says that for two different bifurcation point or the critical point, if your TKJ, that multiplication of that is greater or equal to 0, then and also your alpha naught beta naught 0 is an critical point or equilibrium point, and TKJ is not equal to 0, then there will be an existence of an unbounded branch beam. So now if all these conditions are satisfied, means your crossing number and this spatial number TKJ is non-zero, then I can say yes, there will exist an unbounded branch. Be careful, this is in the Fuller space. Now, using the proposition that we have before, we have proved in our paper, that now I can say yes, not only that, if we take a projection back to our original space, in our original space also, we will get an existence of an unbounded branch. This is the parallel example that we are building. We considered the critical H fixed point space of the critical space, and we will see it is also again discrete. And in this case also, we will see our crossing number is -1. So local result is already done. Now we are approaching for our example for the global result. And we will see in this case also, it is not greater or equal to 0. Of course, -1, it is always 1. And then you can say that yes, in our result also, we are getting an unbounded branch. Now the question is, what is the use of this in our actual real world problem? So here is an example. Think about what I did in a simple one system if you are having a couple of systems. Now the coupling is up to you, how you are connecting. So think about you have a sound system, 1 or 2, say 2 or 3 or 4, and you are connecting in a certain pattern, maybe in a dihedral form or a cement S4 format or whatever. And you want to think about how your sound effect is going on. And you can analyze through this, even if you can say how your sound pattern will come, what the frequency it is, everything you can discuss about this. So here, even if in our paper, we discuss about the same system coupling in a D4 symmetry. And we also go parallelly and we discuss about the orbit, and we said about how the symmetries will go for such system. So this is the application you can work, even if you can think about the neural network, and you can think about how the signal will passes between the neurons and how it will act and all. You can analyze through this system. So these are the couple of references. And yes, thank you for my attending my presentation and giving your attention. And this is the end of my presentation, and I will be happy to know if you have any question.
Thank you, Arnaja Mitra, for the great talk.